going to measure the current that's been consumed by the Sol BLE Tracker here, the average current, by hooking it up to a known capacitance and seeing how much time it takes to discharge a given voltage. And we're going to correct a little bit by just seeing what the leakage discharge is, just with the meter hooked up. And what we should be able to calculate the average charge current of the radio. I want to do the same test, but this time I want to just see what the meter and the internal leakage takes. So we'll time again. And we're running for about 40 seconds. And go. Okay, our beacon time is set to 10 seconds per beacon. I've received a packet. We're at 4.196 volts. I'm going to disconnect it and we'll see how long it takes to discharge. 3, 2, 1. So the first thing I did in my testing was to calculate the impedance of my multimeter, and I did that by grabbing a 10 mega ohm resistor and measured it. It was 10.75. Then I measured a voltage source, 3.319, and I formed a resistive divider by attaching the first resistor to power, the other side to the plus on the multimeter, and the other side of the multimeter to ground. So the multimeter's impedance was R2 of the voltage divider. So then we solve for R2, and the multimeter's impedance calculated out to be 11.0855. And that's pretty much in line with the data sheet. It is a Fluke 87V, and it's supposed to be greater than 10 mega ohms. Now let me just show you the setup. So here is the circuit board mounted on another PCB for stability, since it's made on polyimide film. So we have a capacitor. This is 1,000 microfarad. I measured that capacitor to be 1,107 microfarads with the Fluke 87. And what we're doing is we're measuring the voltage across the capacitor after we disconnect this wire, which is supplying power. So it stays at a steady 4.196 volts until I disconnect it, and then I time it and I record the in voltage, and we use that to we take the difference in energy in the capacitor to work out how much energy was used, and then we convert that to microamps based on time and midpoint voltage of the capacitor. So now let me show you all my calculations. Just a quick note, the firmware that was running on this version only advertises on channel 39. I'm considering changing that because my experiments have shown that when scanning an Android, it can go several seconds without checking channel 39. It'll stay on each channel for several seconds, so there'll be gaps in reception. So I'm probably going to change that to advertise on all channels. And this is all I changed in the firmware. You can see advertising parameters for each test. I adjusted the interval time. So the first one I just simply disabled. I put a comment hashtag and commented out the enabling of the BLE stack. So with sleep, you can see in 60 seconds we drained about 184 millivolts, which if we enter our capacitance into the equation for getting energy from capacitance and voltage and divide by number of seconds, we know how many microwatts. And that ended up spending an average of 14 microwatts roughly. And now we have to subtract the power that would have been drawn by the meter. Now we're going with a low number because obviously if we stayed with a high number, our estimate would be too high. It would be, you know, a sort of a logarithmic curve, but we're only looking at a small section of the overall voltage, and we're looking at the low end, so we know our estimate is going to be conservative, and we work out that the multimeter would have pulled 1.5 microwatts. So our overall consumption was 12.5 microwatts. Now we have to calculate or turn that into microamps. So we take that number of watts and divide it by the midpoint voltage, and we get amps. So about 3 microamps in sleep. Now in the 10-second interval, it drew 5.8 microamps. So 2.8 more than just sleeping. The only problem with the 10-second interval is it's almost impossible to get a device to connect. So while we do have good current consumption in that mode, because it's so hard to connect, we're probably not going to be able to use it. 5 seconds, we're at our target of 10 microamps. So that's roughly where I want it to be, about the consumption to be, is the 5-second interval. But 5 seconds also has that same exact problem. It's very hard to connect to a device that's beaconing at 5 seconds. And I'll tell you as soon as we go through the rest of these what I plan to do. 2.5 second interval gives us 17 microamps. 1 second interval, 40 microamps. 2/3 of a second is about 62 microamps. And now the chart. So if we're comparing current to interval, we kind of got this logarithmic graph here. Obviously, as the interval decreases, current consumption increases. But if we change it from interval to packets per second, you can see we get basically a linear relationship, which is good because that's easier to regress. So if we do a linear regression on this data, we see that we get this line of S-fit. Microamps is equal to 31.45 times packets per second plus 4.2 microamps. So using this, we can extrapolate, and we can see, say, using 0.32 second intervals, we would draw 102 microamps. So ultimately, what I'm planning to do is to use probably the 320 millisecond interval, but I'll burst it for 10 seconds every 2 minutes, because that'll make it really easy to connect to, and of course you'll have to wait for the burst. And I'm probably going to advertise on all channels because of the problem where Android will be sitting there for 7 seconds not checking channel 39, as I determined. Anyway, so that's an update. That's how much current the device draws as opposed to how much it charges under various sun-like conditions. Hope you enjoyed that.